So first off, I'd just like to say, so why are we using C, right? Why use C? Why not use Python or Java or some other language, right? This isn't part of the slides. This is something I want to mention. And the answer is C allows us to see a lot of the lower level instructions that are being executed when we write code, right? So you can look at any C source code and you can look and see, okay, this is exactly what the processor is doing. These are the exact instructions that the processor will be running on it, more or less, right? You don't get that with any other language. And that's the reason why C is so popular in embedded systems, or even an operating system, any kind of lower level programming, right? So throughout the slides, I'm going to make some mentions of where this is really applicable, where you'll see sometimes when the different things that the compiler will do to optimize your code, right, to make it more efficient, can actually break your code. And I'll show you how to fix that, right? So to go over kind of a bit of an outline. So first we're going to talk about files and linkage. We'll talk about the different types of C files and how they're linked together. Then we'll talk about memory. And then we're going to go on to variables and the different qualifiers that we can use to affect these variables. And finally, we'll talk about bits and bytes. So we'll be talking about some lower level stuff. So first off, we'll talk about linkage. So there are two types of linkage. There's internal linkage and external linkage, right? So before I talk about any more about linkage, I'll have you know what a translation unit is. So when I say translation unit, you can think of this essentially as just a C file, right? Or more specifically, a C file and the header file that's included with it, right? Because the processor, the preprocessor, when you compile the code, will just directly include all of the code in the header files that you include in the C file. It'll just essentially just copy and paste that code into your C file, right? So external linkage, this is used for public or global variables, right? The term that we use to denote a variable as externally linked is extern, right? So what this means is that if you define a variable or a function as external or as externally linked, this means that other translation units, so other files, can access and use these variables and functions. Now, internal linkage is essentially what we refer to as like a private linkage. So any identifier, so I say identifiers, I mean functions, variables, etc. These things can only be, if they're internally linked, they can only be accessed in the translation unit where they're defined. And so we use the keyword static to define a variable or a function as internally linked. And later I'll talk to you about the different types or the different meanings of static, because static can actually have two different meanings. So let's talk about the structure of a C project, right? So like I said, C projects are typically broken down into different modules, right? So these are header files and source files. The header files are used to declare any public interfaces. So any functions or variables that need to be accessed in other translation units, in other files, right? Source files actually implement these, they implement the function definitions, and they also will define any global or public variables. So for header files, I'll go over some best practices. First off, you're going to see in all of our code and all of our firmware, you're going to see every header file has what we call a header guard. So what a header guard does, it prevents the header file from being included multiple times in the same file. Because you can see where this would be a problem, where if you include a header that, say you have a header file A, you have header files A, B, and C, right? And a header file C includes A, and B also includes A, and you include in your file C and B. Now you've included a multiple times, and this can cause problems. So what we do is we'll use some preprocessor directives. You see, if not defined my file h, then we'll define my file h, and then we'll have all the code there in the h file. So if this variable, if this my file h is already defined, then we just simply won't include the header file. Okay? That ensures that the header file is only included once. So next best practice is use the minimum number of includes that you need in the header file, right? Keep all your includes in the C files, and only use the amount of the includes. So only include the libraries or other header files in your header file that you need for that header file to compile. Don't define global variables in the header files, right? So only declare them, don't actually assign them values. And everything in the header file should be externally linked, right? Keep your internally linked variables and files in the in your C files. Here we give an example of an externally linked integer, extern int my global, right? That's perfectly fine, a header file. Then you can see a variable definition. So like int my global or in my global equals 7, right? Only use these in C files, right? If you're in the header file, so by default, your variables will be privately linked. So if you're defining variables in your header file, make sure that they should be only global variables, right? No private variables. And don't define, I don't know if you can see my pointer, but don't define your variables in your header files. So for source files, some best practices are, so keep as many of your variables and functions as you can with internal linkage, right? Don't because it's much safer to make sure that to have less things that can access those functions and variables. Less things can go wrong. Right? Any public variables or functions externally linked, right? That's how those work. And always include documentation for all your functions. And so this includes function parameters, function return types, even preconditions for your functions. So here I give a really basic example. This is a function to initialize the I2C module on the board. So here there's no return type, there are no parameters. So all I do is I give a brief explanation. It initializes the I2C peripheral and must be called before using any I2C devices, right? Just a basic overview. But you'll see in our code base, you're going to see a lot of more complex functions with more complex documentation, right? They'll use @brief, @param, which defines a parameter, @return, which is the return value, right? So inline functions, you're define inline functions in your header files, right? You should keep them out of C files. They're defined using the inline keyword. Essentially, what an inline function is that's different from a regular function is it's like a macro, right? If you guys have seen macros in other programming languages, essentially the contents of the file will be copied, or of the function will, not always, but the compiler will try to essentially just copy them into the location where you call the function. What that does is it keeps a function call off the stack, right? So with a really simple function, if you don't need any variables inside your function, right? If it's just a simple return, some return expression, then it allows you to still use the still have the features of calling a function without having to actually put a function call on the stack, which I'll talk more about that in a few minutes. So it saves memory, essentially. I won't go too in depth on exactly why you use it, but sometimes you'll want sometimes you're going to want to use inline functions because you can have different definitions on different platforms, and that gives you the functionality to do that. But I'll just kind of wave my hand at that. So now I'm going to talk about memory. So first, we'll talk about stack versus heap, right? So stacks and heaps, they're just data structures. That's all they are, right? So a stack is a linear data structure. That means you can't access data on the stack however you want to, right? You can only access the data on the very top of the stack, right? So we use a stack for function calls. So every time a function is called in your code, what we'll do is we'll stick a new entry on the top of the stack, and that will include all your local variables along with some other miscellaneous data that I won't go into. So when we refer to the stack, right? We hear a lot of talk about the stack. We're referring to the call stack, or the stack that contains all the function calls on them, right? So I use the term here, FILA. It means first in, last out. That's how a stack operates, right? So the first element to go in the stack is the last to go out. So the data essentially expands. They stack one on top of the other, and then you can only remove the one on the top, right? For the heap, so now when I talk about the heap, again, a heap is just a data type. But when we talk about the heap, we're talking about the area in memory where we store memory, like dynamic variables, essentially. So the heap is nonlinear. It's really useful for dynamic memory allocation because there's no access order. So you can access any address you want in the heap at any time. Right? We use this typically in C for runtime memory allocation. So that means allocating and deallocating memory while the program is running. However, on our system, we're going to we really try our best to avoid any kind of runtime memory allocation for reasons that I'll talk about in a few minutes. So I mentioned runtime memory allocation. We refer to that as dynamic memory. But what else is there then, right? The other type of memory allocation is static memory. So static memory, and I won't go too much into this because I think Julian will be talking about this in the next module. But static memory is it's allocated by the compiler when you compile your code. So static is stasis, it means at rest, right? So the size of a static variable or static memory block is defined at compile time, right? This is so you may have heard the term a static array before, right? A static array is an array that has a fixed length, right? So if I define an array here, you see int array static or r static is equal to, and I give it the values of 1, 2, 3, right? Or 0, 1, 2, 3. So that's an array of size 4. You can't increase or decrease that array size while your program is running. Now, with dynamic memory, and here I give an example of how typically we'll use dynamic memory. Dynamic memory, you can allocate whatever size you want while running, right? So you could have a variable size. You could ask the user for an input, say, give me an array size, and I'll input a number. Say I'll input the number like 20, right? And you can allocate an array while the program is running of size 20. Again, we try to avoid this, right? Because I think I mentioned this later on the slides, but a big problem with dynamic memory allocation is that you never know, on a microcontroller especially, you never know if you actually have that memory there to allocate. Right. So this resides in the heap. And I have a little warning here, dynamic memory must always be freed. If you don't free your dynamic memory that you allocate, what you'll do is you'll keep using up memory. You won't get any of that memory back. Eventually, there's a good chance you'll run out of memory. But hopefully you won't have to worry about this, because hopefully you won't be forced to use dynamic memory allocation on the TMS 570. Right? Avoid that at all costs. So I want to go into a bit of how structures are aligned, right? So a struct, so first off, if you don't know what a struct is, essentially it's just a data type that you can define that includes a bunch of other data types or a bunch of other variables inside of it. So these variables inside the structs, they must be aligned to their data type sizes, right? What that means is essentially the index at which that specific variable starts in the code, or sorry, in the memory, must be a multiple of the size of that variable, right? So a char can only be positioned, it can only be aligned at a memory index that's a multiple of 1, which is any memory index. But an integer has to be aligned at a memory index that's a multiple of 4. And that can create problems and inefficiencies in how we store the data in memory. So if I look at these structs, you'll see that they have the exact same, can you, actually 1 second, can you see my mouse?
It's visible.
Okay, awesome. So
if you hit L, Ethan, you get a laser pointer.
L? Oh, awesome, thanks. Okay, that's better. So if you look at these two structs, you'll see they have the exact same contents, right? The only difference is here, the pointer to a character, right? This char star P is moved to the top of the struct, right? You see that? So, but the sizes of these two structs are different, even though they have the exact same, you'd think that they'd have the exact same size because they have the exact same memory contents, right? This is because if we go through, let's on the next slide, I have a diagram of this here. So if we look, so first off, here we have the what we call an unpacked struct, right? This is, so we start off with an integer that's aligned to the index 0. That is 0 is a multiple of 4, right? Divisible by 4. So that's fine. Now we have a short, which shorts are 2 bytes in size. So is 4 a multiple of 2? Yes, that's fine. Now here we have index 6. So at index 6, we're trying to put a char star, so a pointer to a character. So a pointer to anything in a 32-bit system, and remember the TMS 570 is 32-bit. A pointer to anything is 4 bytes, right? It's 32 bits. So is 6 divisible by 4? Nope. So what we have to do is we have to pad it with this is just any memory. This is just unused memory here. We have to pad it so that we can start our pointer at index 8, right? And again, if you go through the same logic, you see, okay, these chars can be anywhere. Chars never need to be padded. And then we actually have to pad the end of the structure as well, because all structures must end on a multiple of 4, because we're on a 32-bit system. Right, on a 64-bit system, it have to end on a multiple of 8, right? Now, if we look at this simple change that we made, all we did was we moved the variable to the top, right? You wouldn't think that would make any difference, but it does. Now the pointer is at the top, and now everything, all the variables, they are perfectly aligned to their data, to multiples of their data size, right? 0, so 0 is a multiple of 4, or it's divisible by 4. Then 4 is divisible by 4, 8 is divisible by 2, 10 is divisible by 1, 11 is divisible by 1, right? So we actually save 4 bytes here just by rearranging the structure. Now you can have the compiler do this automatically if we use this this modifier, say __ attribute __, you can see it here, packed, right? So you put that right before the struct, right before the struct definition, and that will pack your structure. Actually, I'm sorry, I'm pretty sure you put that before the identifier. That's a mistake.
Just want to jump in there with one extra
Yes.
clarification. Adding this packed attribute, it won't reorder the fields in memory. It'll just eliminate the padding bytes. And so you have to, not all hardware will support not having padding bytes. So you do have to be careful if you're going to be using this packed attribute.
Thanks. So I want to talk about, so before we finish off talking about memory, I want to talk about the difference between Little Endian and Big Endian memory. So first off, what does Endian mean, right? So Endianness determines where bytes are stored in memory, right? For data types, I should say, for data types that have multiple bytes in them, right? What that means is, imagine in memory you have, so I show a little diagram here. You have at index 0, you have some byte. So let's say 0A. Index 1, you have 0B, 0C, 0D. If that's a 4-byte variable, then which byte is which, right? So which byte is the first byte and which byte is the last byte? Or in more technical terms, which byte is the least significant and which byte is the most significant, right? It may sound natural to say, okay, the 0th byte is the least significant. But as the saying goes, the best thing about standards is there are so many of them, right? So many to choose from. So it may sound like, oh yeah, let's all disagree and say that the 0th byte is the least significant byte. But sadly, for technical reasons, we can't do that. So we have Little Endian and Big Endian systems. Now the TMS 570 memory is Big Endian. So what that means is that the 0th byte, so the first byte is actually the most significant. So if you're reading through memory at index 0, index 1, index 2, index 3, index 0 would be what you would consider the leftmost if you were reading it on a piece of paper, right? It's the most significant byte in the data type, right? Of course, Little Endian is the other way around. So now I'm going to talk about variables and qualifiers. So first off, let's talk about the different qualifiers that go into a variable definition. So I'm going to talk about 3 main ones: static, auto, and volatile. So I mentioned earlier that static has multiple uses. It has 2 different meanings. And now I'm going to explain exactly what I mean here. So when you use static inside of a code block or a function, let's say, that means that you're saying that this variable actually will not reside in the stack. This variable will reside in program memory, and it'll persist between function calls, right? So say you have a function and you have a static variable. Say you have I almost should write this down. But say you have a static variable that counts. Let's say it starts at 0, and then every time you run through the function, you add 1 to that variable. Every time you call a function, that variable will increase by 1. Right? This results in some kind of unexpected behavior, or I shouldn't say unexpected behavior, but it can result in unexpected behavior if you don't know exactly what you're doing. So, and as a general rule of thumb, avoid using static variables inside of code and code blocks or functions. Now, when you use outside of functions, it means something completely different. It means that the variable is internally linked, right? So that means it's a private variable. No other files or the technical term is translation units. No other translation units can change or read this variable. So auto, this is the default for variables that are defined inside functions or code blocks. And all that auto means is that when the code block or the function finishes executing, all the data in the variable will be lost, right? So what's actually happening here is the variable is going to be stored in the stack, right? Remember, we talked about the stack. And as soon as the function call is over, it gets popped from the stack and it's lost. This is what you typically see with these variables or what we call local variables inside of functions. So you're probably quite familiar with auto variables. You just never knew that they were called auto before. So last, but probably most importantly, is volatile. So volatile is very important, especially in embedded systems. Now, all that volatile is doing is it's affecting how the compiler optimizes the code, right? Remember in the beginning of this module, I mentioned that the beauty in C is that you can see the individual instructions that are created from the code that you write. Well, here's where that becomes really important to know that. So here's an example in the bottom right-hand corner. You can see an example of some code that is very wrong without defining the variable as volatile, right? So imagine you're waiting on some kind of, so you have some memory mapped input or input MMIO, and you're trying to wait for when the value of this memory address turns to 1, right? Goes high. So this code probably looks right to you, right? So you have a pointer to this data, to the data that you're waiting for, and then you have a while loop that waits until every loop of the while loop, it's dereferencing this pointer, and it's checking to see if it's 1 yet, right? As soon as it's 1, it'll break out the loop. But this is completely wrong, because the way the compiler will actually turn this code into individual instructions is what it's going to do is it's going to say, okay, here we have this pointer to an address. So, and then we dereference it. So let's grab the memory. The first thing we're going to do is we're going to read the memory at this address. And then we're going to go into a while loop waiting. So it's going to store that in a register. So it's going to store that somewhere locally in the program. That's not going to change. And then it's going to go through this while loop, and it's going to keep checking to see if it's equal to 0. So if at the time that you go into this while loop, it's equal to 0, your while loop is going to go on infinitely, right? All you're doing is you're only reading that memory once, because the C compiler is going to say, okay, memory multiple times. Why bother reading the memory every single loop of the while loop, right? Reading memory is a very slow process, right? So you're going to get an infinite loop. The solution to this, this is a compiler optimization, right? The compiler is doing this because the compiler looks at the code. It says nothing else is changing the value at this pointer, right? It doesn't see anything changing it. So let's just assume it doesn't change. Of course, that assumption is wrong, right? So when you add the volatile qualifier, what you're doing is you're saying, okay, this data may change at any time outside of this translation unit, outside of this file. The compiler may not know it, but this data can change at any time, right? So then the compiler is going to look at this code and say, okay, well, since the value at this pointer can be changing at any time, then we're going to have every single loop, we're going to have to dereference the pointer again and read the data again and check, right? So this code example here is completely wrong. You need to add a volatile, the volatile qualifier to it. Okay, so where do you add the volatile qualifier, right? At the beginning, do you add it before the uint8_t? Do you add it after? Do you add it after the star, so after the asterisk, but before the preg identifier? Right? Where do you add it? There are a bunch of places you could put it. That's where the right to left rule comes in. So the right to left rule tells us how to read any variable declaration in C, right? This may sound simple to say, oh, well, I can just memorize the orders. But when you can get really nasty variable declarations, which I'm not going to go into, and the right to left rule will solve them perfectly. So here's the question for you guys. So what's the difference between all of these declarations, right? I got 4 declarations here in the top left-hand corner. So let's use the right to left rule. So let's start with the first declaration, myvar0, right? Myvar0 is a pointer to a volatile integer, right? What that means is that the pointer is pointing to an integer that's volatile, right? myvar1 is a pointer to an integer that is volatile, right? Exact same thing. So whether you put the volatile before the type definition, so before int, before uint 8_t or any other type definition, or if you put it after, you get the same thing. Now, what about the third case, myvar2? Myvar2 is a volatile pointer to an integer. You see this, there's a subtlety there. This is saying that the pointer is volatile and not the integer. So it's not the data that you're pointing to that's volatile, but rather it's the pointer, it's where we're pointing to, right? It's that address in the pointer that's volatile. So as a rule of thumb, this third one, myvar2, typically this is very rare. You don't see this very often, right? So I'm going to say for all intents and purposes that if you define your variable as a volatile pointer, you probably defined it wrong. So you'll almost always stick to the first two. And here's an even rarer case, myvar3. So myvar3 is a volatile pointer to a volatile integer. Right? So that's incredibly rare. You almost never see this. But I thought I'd put it in there just to show you exactly the differences between a volatile pointer and a volatile integer. In this case, both the pointer itself and the memory it's pointing to are both volatile. So we'll talk about the strict aliasing rule. So first off, what is aliasing, right? Aliasing is when two pointers point to the exact same location in memory. The strict aliasing rule says that if two or more pointers point to the same place in memory, they must be the same type. So you can't have a char pointer, or actually, sorry, you can't have an integer pointer and a short pointer to the same location in memory, right? That would be a violation of this rule. Right? The one exception is a char pointer actually is allowed to alias other types. And I'm not going to go into why this is. It's because it's necessary for some implementation of system functions. Right? So why does this rule exist? Well, I've got a little code sample here, and I'll show you why. It's used, again, it's used for optimization, right? This is where that whole idea of knowing how C converts your source code into exact instructions matters, right? So here I have a function called foo, and I've got a pointer to an integer and a pointer to a long as parameters. So what I do is I'll dereference the pointer to the pointer 1, and so I'll set the pointer 1 value to 10, right? The value at the memory address, and the same thing for pointer 2, right? Simple enough. Now, the problem here arises when I have a variable and I give it, so here I'm violating the strict aliasing principle, right? The strict aliasing rule. So I'm actually casting this so I'm getting a pointer to this variable A, and I'm casting it to an integer, to be an integer pointer, a pointer to an integer. And here we have a pointer to a long. They're both pointing to the same place, yet they have different types, right? The problem here is that the C compiler is going to look at this, and the C compiler is going to say, okay, an int is different from a long, and therefore we're going to assume that these pointers point to different places. So what the compiler will do to optimize this is it'll say, okay, pointer 1 is defined, the value of pointer 1 is defined at being 10, and then we're going to dereference and read the value at pointer 1. So this will always return 10. So the compiler is going to say, okay, let's just cut this all out because this is just a waste of time right? Let's just return the value 10, right? We don't need to do a memory read at pointer 1. We don't need to read the because we know what the memory is. It's going to be 10, right? We just set it to 10. Right? The problem here is that we also set it to 11. But the compiler doesn't know that because it thinks that these are different. So you can actually disable this rule, right? You can disable this rule and it won't optimize out this pointer dereference, right? But for our project, we're going to maintain this rule. because it is useful for optimization, and it's very rare that you'll want to alias pointers with different types, right? So C is doing this. C isn't making this rule just to be mean, right? It's not just an unnecessary rule. It's used for optimization, right? So if this was an integer pointer here, right, then the C compiler will say, okay, well, they're two integer pointers. They very well could be pointed to the same place. It won't assume they're pointing to different places, and it won't optimize out the dereference, right? So this is a more advanced topic. It's probably, it may not be something that you'll encounter a lot, but I think it's useful to know. Okay. Before I move on, do we have any questions? Am I moving too fast or too slow?
All good here.
Okay, just checking the chat here. Okay. Okay, so on the previous slide, would the aliasing rule not apply if one of the pointers were char? Let's go back to that. So yes, I believe it would be fine. So let's talk about bit masks now. So what is a bit mask? Well, a bit mask is a series of bits, right? With each bit representing a Boolean, right? This could be anything. This could be true, false. This could be on or off, right? Oftentimes you'll see, oftentimes we'll see this used for configuring microcontroller hardware, because it allows us to set a certain setting on or off, right? Like enable open drain or disable open drain. Right, so this is how almost all the hardware on our microcontroller is configured. It's also used for other functions such as GPIO, right? So forcing a pin high or low, where 1 would typically represent high and 0 would typically represent low. Right, so I'm going to show you an example now of turning an LED on and off with the GPIO. Next slide, I will. I think. Yeah, sorry. Sorry, in a few slides, I'll show you that. Here's an example of a GPIO here's an example of a hardware register that's represented as a bit mask. So this is an excerpt from the TMS 570 technical reference manual. So you can see here, bits 31 to 8 are unused, right? As the description says, so reads return 0, writes have no effect. So you should never have to access these bits. Now the first 8 bits of this register represent the high or low states on each of the pins in the GPIO. So bit 0 would represent the first GPIO pin, which may not necessarily correlate directly. You have to look at the data sheet to see where the exact pins are on the TMS 570 chip. But this means on the port that's specified. So if we say, and I'm going to show you a better example of this now in a few slides, like I mentioned. But if we use GIO dout A, you can see there's a little N there in the field value, or in the field name, I'm sorry. So we say GIO dout A, and we set bit 2 to be 1, then that means we're setting the third pin on the port A of the GPIO output to be high. I'm sorry if that sounds really confusing, but I'll show you a concrete example in a second. first I want to mention the bitwise operators. So we use these bitwise operators to manipulate bit masks, among other things. So we have 6 operators in total with bitwise and, bitwise or. So and is simple. 1 and 1 is 1. 1 0 0 1 is 1, and 0 0 is 0. Right. So it's 1. Or sorry. I'm sorry. 1 and 1 is 1, and everything else is 0. I'll show you. I'll show an example of that. So bitwise or is just 1 bit or the other bit. If one or the other bit is 1, then the output will be 1, right? A bitwise and 1 bit and the other bit, then you get 1 as an output. So 1's complement is just the inverse, right? So that little tilde is used to invert all the bits. So a 0 becomes a 1 becomes a 0. Then we have shift right and shift left. So shift right takes all the bits and shifts into the right, and shift left takes all the bits, shifts into the left. And I will mention in a second that you need to be careful when using these, the shift right and shift left, because there are specific different implementations depending on what variable and depending on what variable you're shifting, and also depending on what compiler you're compiling your code with. So you have to be really careful using those. And an exclusive or, right, is 1 or the other, but not both. So 1 and 0 or 0 and 1 would both give you an output of 1. So I got some examples here. So 1 0 1 and 1 0 0. Can someone put in the chat what the output of this would be? Yep, 1 0 0. That's correct. What about 1 0 1 or 1 0 0? Yep, that's correct, Montikim and Aswin. What about not 1 0 1? What about a left shift? So what about a left shift of 1 0 1 by 2 bits? So that's right, Montikim, but remember, so I'm gonna assume that we have a 3-bit variable here. So you'll lose the top 2 bits, right? So 1 0 0. Yeah, they're both technically correct. Yep. Here's an interesting case. There's a very interesting case. What about 1 0 1 right shifted by 1? So here's where this is interesting, and I'll talk about this in the next slide. So some compilers will actually sign extend. So rather than 0 1 0, right, Montikim, you'll get 1 1 0. Right, and the reason they do this is because in 2's complement, if you have a 1 in the most significant bit of your variable, that actually means your variable is negative, right? So if you have a negative variable, I'm sure, I don't know if are you guys familiar with the concept that a right shift can represents a division by 2, and a left shift represents a multiplication by 2, right? Okay, so do you see the problem here? If you have a negative, and I'll do that. So if you have a negative variable and you do a right shift by 1, now all of a sudden it's positive, because that bit goes from 1 to 0, right? So what you're actually expecting, or what you were expecting if you meant for that right shift to be a division by 2, is you were expecting for the number to be still negative, right? So that's a So some compilers will actually sign extend. So if you're looking for a bitwise shift, if you're looking for a pure bit shift, then you're going to be really confused when that top bit, that most significant bit, is still 1, right? So for that reason, and I'm going to go into this a bit more in the next slide, but for that reason, we say you only do bit shifts on an unsigned variable. Before I jump into that, what's 101 XORed with 100? Just stick it in the chat. Yep, that's right, 001. Okay, and here's what I was talking about with left shifts and right shifts. So as a rule of thumb, only use these bitwise shift operators on integers and data types that are unsigned. Right? Because on a signed integer, it can have the implementations can be different. The worst part about it is different compilers can implement these differently. So you could get unexpected results. Like, here's a little example I give. So 100,001, that's minus 127. So if you want to divide that by 2, you do a right shift. The compiler will shift that all right, and you'll get this. You'll get the value, the whole thing shifted to the right by 1 bit, and then the compiler will say, okay, well now the uppermost bit is a 0, right? But you would expect that in a pure bit shift, but the value is negative. It should still be negative after dividing by 2. So let's stick this 1 here. So let's assume that you were trying to do some funny thing with configuring your hardware, right? Say you have a bunch of LEDs and you want to like toggle each one on, or you want to have like some kind of like wave of them, of like this LED's on, this LED's on, these 2 are off, and then you want to shift the configuration so that now this LED is on, this LED is on, and these 2 are off, right? You're going to get a weird behavior because now this LED is also going to be on, this LED would be on, this would be off, this would be on, right? It's a bit of a funny example, but you're going to get unexpected behaviors to take away, right? So make sure that you're using unsigned integers when you're doing left or right shifts. So here's a quick little example, some example code of enabling an LED pin using an OR operation and disabling an LED pin using an AND operation, right? So you can look over those. I won't go into detail on there, but those are little examples of the practical uses of bitwise operators. Those are the examples that I promised you a couple slides ago. Are there any questions about that? Oh, yes. Oh, yeah. I saw your questions, Julian. Yeah, I see. So I want to go over some basic design guidelines. So first off, avoid dynamically allocating memory unless you absolutely have to, right? Don't use malloc or free in any of your code. Like I said, the big problem is that you can run out of memory, and we will run out of memory really quickly on an embedded system. This is not worth the hassle. Stay away from it. Use internal linkage as much as you can, right? Don't make any variables that don't need to be global, right? Stay away from global variables. The less things that can access your variables and functions, the less problems that can happen. Always use volatile when you're accessing hardware registers, right? Because hardware registers, like I said, they're changing asynchronously. So your compiler won't know that it's changed, but they'll change. So then you'll get really weird and difficult to debug problems. You'll spend a lot of time trying to fix those problems. always use explicitly sized data types, right? So you're going to see in our firmware, we use a lot of uint32_t, a uint8_t, uint16_t. We don't use any ints. We don't use any just int. We don't use any floats, doubles, any of that, right? Because ints, they can have different sizes and different systems, right? It's not consistent. It can cause errors. And another thing, always pass structs to functions by pointers, right? So you know that arrays won't get copied. If you pass an array to a function, it'll only hand up pointers to the array, right? And the reason they do that is because you don't want to copy the entire array onto the stack, because your stack can have a lot limited memory. And if you copy an entire array into the stack, your stack can overflow, right? You'll run out of memory in the stack. So C automatically does that with arrays, but it doesn't automatically do that with structures. So you're going to have to do that yourself with structures. If you just hand a structure to a C function call, it's going to copy the entire structure and all the memory in the structure. And you can, on an embedded system like ours, you can run out of memory really quickly. Finally, I want to talk about MISRA. So MISRA is something you're going to see when you're writing C code for our firmware base. So MISRA is the Motor Industry Software Reliability Association, and this association defines a set of programming standards that improve the reliability of a software base, right? So it's basic. It's a lot of good practices and basic guidelines that help ensure that the behavior of the system is well defined and prevent potential bugs. Most common violation you're going to see is exactly what I just mentioned. It's using generic types. So, like I said, in our firmware, we're always using explicit types. If you use a generic type, MISRA is going to complain when you go to compile your code, and you're going to get a warning in CCS. So it may be tempting to ignore all these warnings, but don't, because we will check them through code review. And if you need any help with some of these warnings can be a little harder to understand. If you need any help with those, feel free to message any of us or message the Slack channel, and we'll help you ensure your code is MISRA compliant. And that is the end of the slides. Do we have any questions?